Geophysics, Engineering and Environment, from theory to practical applications. Today, we are in the day 3 of this event. And now, before we begin, let me introduce myself again. Indra Gunawan from Geophysical Engineering ITB. I am the chairman of this session. And let me remind you one thing, that this event is organized by ITB. We partner with some universities in this event is coordinated by Dr. Wahyudi from Geophysical Engineering ITB. And this afternoon at this session, joining us today is an expert from Chiba University, Professor Atsushi Higuchi. And today, Higuchi Sensei will give a lecture about meteorological for weather observation. And I will share the profile of Higuchi Sensei. Sorry. You can see on the screen that this is a profile of Sensei. Higuchi Sensei is associate professor from Chiba University. I'm sorry. And currently he is for environmental remote sensing, Chiba University, Japan, and in the Graduate School of Science and Engineering, Divisions of Earth and Environmental Science, Department of Environmental Remote Sensing. And his expert in hydrology and also satellite climatology. He is active in several organizations such as Japan Society of Hydrology and Water Resources, Japanese Association of Hydrological Sciences, and also the Meteorological Society of Japan, the Remote Sensing Society of Japan, the Association of Japanese Geographers, Japanese Geoscience Union, and American Geophysical Union. And today, he already have more than 70 publications that indexed by Google Scholar, with more than 500 citations. At the right section of slide, you can see the brief background of Higuchi Sensei. And then this is the latest publications and also the latest projects of Higuchi Sensei. And now let's welcome Professor Higuchi. Higuchi Sensei, it's so good to have you here. Thank you so much for joining us. Okay. And when I read at your profile, I saw that you're active at project. And it reminds me when I was participating in the spring school at 2015, I think. That activity is coordinated by Yoden Kyoto Daigaku, and we have several days in Ekti Plaza Biwa. I think you know that place, and it is a beautiful place, I think. Okay, now let's start our class. Higuchi Sensei, you have about 1 hour and 15 minutes to your lecturer, and following with 20 minutes to discussion. Please, those are your results.
Okay, thank you very much to introduce me. So my name is Atsushi Higuchi, and from Chiba Universities. And I'm also colleagues of the and Yosafato-san. He is and good friends. And also I'm talking about today. And okay, let me start. Can you see my slide?
Yes.
Yeah. So, and I will talking about and originally title is a meteorological satellite for weather observations. But today, I will talking about more and limited versions. And firstly, I insert the geostationary meteorological satellite for the weather observation, and another purpose I will introduce about utilize the geostationary meteorological satellite, because this third, I will say that and say later, the third generation the geostationary meteorological satellite is a powerful eye to capture the Earth with high temporal resolutions. I will show later. So, and today's content is very simple. And firstly, I introduced brief introductions about the geostationary meteorological satellite. So-called short name is a GEO. So, and I will be talking about and lecture like the brief introduction about the GEO, the how to monitor the weather's conditions by the GEOs, and with the several examples. After that, and I will be talking about the third generation GEO. This is latest versions about the geostationary satellite. So, and in the period of the third generation GEOs, so firstly, I will be talking about how advanced and compared with the second generation or previous versions. And the second topics, I will be talking about what kind of events can capture by the third geostationary satellite. And thirdly, I will be talking about how utilized. So I will demonstrate, show some example by our group or some review result. After that, I summarize the closing remarks. This is my today's talk. So, and firstly, a brief introduction for the geostationary meteorological satellites generals. So, and firstly, and most of people imagine the satellite is rotate the Earth with the polar orbit. This is most of people can imagine the satellite case in the case of the Earth observation satellite. So the left side movie is and virtual movies of the Earth and rotated with around the Earth and organized by the NASA or NOAA. So many satellites is orbit with a polar orbit is like this. So on the other hand, another satellite also can capture the Earth face. So, and the left picture shows the two level satellite. One satellite is a polar orbiting satellite systems. This is a very famous one. And the other one is surrounding such kind of the low orbit satellite. We also have with a so long distance and the same locations and satellite. This is a geostationary and elevation satellite. So this is the first step. So, and I will talking about this is a spatial resolution and the altitude of the platform. This is a schematic illustrations. Sorry, the partly is written in Japanese. And the low elevation satellite is associated with another word, the polar orbit. This distance from the Earth's surface to the satellite platforms, its height is approximately the 700 or 800 kilometers from the Earth's surface. This is the height is balanced with the gravity of the Earth. So the height of the 700 meters or 800 kilometers, this is and balancing with Earth's gravities. This is low elevation satellite. The other hand, the written in here is GEO. Geostationary satellite, its height is more higher compared with the polar orbit. This is 36,000 kilometers. This is approximately same with the length of the equator of the Earth. Very long distance compared with the low elevation satellite. So this is also balanced with the gravities. So I will show the okay. So this is a schematic illustrations and to explain the geostationary satellite. And the left pictures show the hammer throws players. He is the Murofushi-san and famous and hammer throws players in Japan. So this is kind of the analogies, the geostationary satellite. Hammer throw player is the Earth. And here is a hammer, you can see. So, and wire is a kind of the balancing with the gravities and so far from the Earth. So, and geosensors is located here. So, and hammer throw player is rotated just before the throws and hammer. It's very easy to imagine, just before the throwing. So this, if this hammer, this is a kind of the geostationary sensors bus. Here is the sensors and installs. So these sensors always can capture the Murofushi-san's face. It is always the same face captured. This is a big advantage of the geostationary observations Earth satellite. So, and the captured image shows this slide. So, in the case of the capture, the geostationary and environmental satellite, the geostationary meteorological satellites captures the road and Earth's face. Every time, the always can capture the same face. So this is important things. Japan's operations, the Himari satellite cannot capture the American continent. Always captures the Indonesian and maritime continent. So, and that's the reason why to the and geostationary observation satellite. So what is the advantage compared with the low elevation satellite? And one of the advantage of the geostationary satellite, and this is increasing the frequency is observations interval, at least more than 3 hours. This is and captures 4 geostationary satellites data's movie. So here is the FY2D. It's the Chinese geostationary meteorological satellite. This is the previous version. And the MTSAT-2 is the Japan Meteorological Agency's operated the geostationary meteorological satellite. And the GOES series is operated by the United States at north, GOES west, and GOES east. So if we want to capture the whole of the globe by the geostationary satellite, at least 4 or 5 geostationary satellites will be required in the whole of the Earth's surface, combined with the 4 or 5 geostationary satellite data capturing. So each geostationary satellite can get the data in the initially from the first stage of the geostationary satellites. Once per 3 hours can get the data. But the latest version becomes the time is also shrinking. But anyways, compared with the low elevation satellite, it's also very easy to capture the short time phenomena like a weather, very easily to capture by the geostationary meteorological satellite. So this is the reason why the meteorological agencies operate the geostationary environmental satellite. This is the purpose of the weather's observation, is the primaries and the task to operate the geostationary meteorological satellite. So, and okay, so this is an example of the typical and observations channels and boarded on the geostationary meteorological satellite. Okay, step by step, I will explain these things. So, and left ones shows the IR1. This is a 10 micrometers wavelength. This is all geostationary meteorological satellite boarded on these channels. 10 micrometer is the window of the atmosphere. And the main peak of the Earth's radiation center wavelength is also the 10 micrometers. This wavelength very useful to observe to the surface conditions, surface temperatures conditions. This is not only for the weather's observations, but also the surface conditions, because absorption's band is not so the, and measure and absorption's band is not so here. So, and this and grayscale colors movies represent the lower temperatures case is assigned color become to the white, and higher brightness temperatures represent to the black. This is a sense of the opposite, is a grayscale and coloring, because most of people's easy to imagine cloud is white. So to say another word, 10 micrometers IR1's image easily to visualize the cloud behaviors, because and high developing cloud is the height is very high. To the basically atmospheric temperature is vertical profile of the atmospheric temperatures decrease with the height. So, and this meaning to the and the 200 Kelvin is a very quite low temperatures, means the highly developed cloud can capture by the 10 micrometers IR image. So in fact, in such movies case, your countries, Indonesian countries, as you know, it's so the highly convective activities occurs due to the warm pools areas. And to thinking about the Hadley circulations, this is here is the upwelling motion is dominant. So diurnal variability of the cloud is a dominant factor and around the Indonesian countries, tropic regions. So here you can see the relatively low temperatures observed. This is represents the cloud activities. On the other hand, and here is subtropical areas. Here is the subsidence zone. Thinking about the Hadley circulations, global circulation of the atmosphere. So like and Western Pacific and subtropical zone is relatively temperature is high because of the subsidence of the atmospheric motions. So the suppressing the convections. This is also can captured by the 10 micrometers images. And the mid-latitude, like Japan, this here is the Rossby waves propagations can capture by the low and high is passing. Such kind of behavior is easily to visualize as a proxy of the 10 micrometers brightness temperatures. So that's the reason why the most of and the TV program also the programming to the assign the movie shows to the geostationary meteorological satellite data, at least in Japan or in US. This is very easy to visualize in the large scale, the cloud activities as a proxies. So this is a measures band, 10 micrometers. Is this okay? Okay, let's move on to the next and the band. This is a water vapors band. The center wavelength is 7 micrometers. And I will mention later, the old and the second generations geos have this band. This 7 micrometers and wavelengths is sensible for the water vapors in the atmosphere. This is wavelength is a kind of the indicator of the how many is water vapor available in the atmospheres. So compared with the 10 micrometers and the 7 micrometers image, and here is the 7 micrometers image. It's the more, and how to say, the black and not so the black and white. This is a kind of a grayscale image compared with the 10 micrometers. So these things and interpreted by the water vapors is also the reducing the brightness temperatures in the 7 micrometers. This is the indicator as water vapors in the atmospheres. So this and the 7 micrometers image to see the movies carefully is compared with the 10 micrometers movies, easily to imagine how to move the atmospheric and motions by the proxy of the water vapors. So here is a rotate like this. Here is moving. Atmospheric motion is like this. So very easy to the monitors how to the atmospheric and movement can easily to visualize compared to the 10 micrometers. So this image can help for the expert of the meteorology and the observatory in the weather. That's the reason why the 7 micrometers and wavelengths installed in the geostationary satellite. And IR4 is the 2.5 generation satellite can capture. This is 3.5 and 4 micrometers. This wavelength is both sunlight wavelengths and the Earth itself, the emitted wavelengths, both two and wavelengths is always affected. So that's the reason why it is and here is a darker and lighter, darker is lighter. So day and night contrast can observed, but in the case of the visible wavelengths, during the night time cannot be used. But these short waves and infrared radiometers and 3.5 and 4 micrometers both and the sunlight and the Earth itself emitted wavelengths and also influenced. So this is very interesting and wavelengths. So this wavelength is and suitable for the and relatively low-level cloud detections. So this is an example for the typical observations channels in the geostationary meteorological satellite. So this is the basic information. Okay. So, and such kind of the geostationary observations and generations is the we say the first generations and the histories and the first generation is the one thermal infrared 10 micrometers wavelengths and the one visible band. Only the 2 channels is available, and the 1.5 generations have the one thermal infrared 10 micrometers, one water vapor channels, and one visible band is available. The second generation is so-called the and GMS5 or GOES second generations, and the Meteor and MTSAT series is the 2 IR, 2 thermal infrared and 1 water vapors and 1 visible wavelengths. And the 2.5 generation is the 5 IR and 2 microwaves and multiple and visible. It's like this. And such kinds of and histories is occurs. And the initial stage is more and early eras. We only have the first generations, and also increasing the observations band like this. And recently, we also have the third generations, and like the Himari 8 and GOES R and GOES S, as I will mention later. This is and history is global observations. So, and I will talking about is how to analyze the optics and thermal infrared band or something like that for the and weather observations. So this is 2 ways, and I show the examples. In the first thing is a simple image analysis for the diagnose the target cloud. So, and the first one is so the detection of the convective activities. To say the another word, cloud is the thermal IR. And the detection of the low-level cloud by the visible wavelengths. And another thing is the moving convection features. This is a kind of the I mentioned later as the Hofmiller diagram. This is popular in the meteorology. And another and possibilities then detect the cloud is a multiple, as I say, another was a combination usage of the several band or several channels. And one thing is a combination of the 2 thermal infrared. This says the split windows technique I'll mention later, and combinations of the visible and thermal infrared for the classification in the cloud type. And the third one is not the popular one, but the combination of the water vapor channel and the thermal infrared. Okay, I'm talking about these things step by step. So firstly, I show the global distribution of the and globally merged geostationary satellite data with the how many percentage of the and brightness temperatures and cloud frequencies. And this is a kind of a proxy of the cloud activities. This is very simple. And a kind of the threshold we determine. After that, lower than the threshold we count. So how many number is also observed in the total period. So in such case, you can see in your country is the highest frequency is so the and a kind of threshold and more than the 35% around here. And also you can see the and ITCZ likes a belt and the intertropical convective zone and the belt you can see. And how to say it, and meridional and contrast in the Pacific Oceans. And warm pool is relatively high, and the near of the and South America is relatively and frequency is very low because of the low level cloud. It's here is dominant. So, and even though this is one channel's data analysis, we can see the climatological features of the cloud coverage. However, this is not the actual coverage of the cloud cover because this is based on the brightness temperature threshold method. In fact, here is a Tibetan plateau is more than the 4,000 meters in elevations, very high land. During the high land in winters, surface temperature is also extremely become to the lower. So this is misdetections of the cloud count around here, and also Siberian regions. Here is also the cold temperature, surface temperature is misdetected as the number of the cloud detections. This is a minor problem. But however, and even though the cases in the tropics and the threshold method is so effective to the how many cloud is covers and to diagnose the cloud activities. So such of things is and applied into the cloud activities monitoring research. This is one example is Fujinami and Yasunari's 2001 is a Journal of Meteorological Society of Japan. So this is a geostationary satellite data analysis for the Tibetan plateaus convection activities. So, and the famous one is the Convective Index, so-called IC. And originally, this is proposed by the Nitta and Sekines. So he says the and Convective Index, if the brightness temperature is less than the 250 kelvins, this is a detection of the convections. So in the case of the and less than 250 is a 250 minus TBBs. So the and the depth of the convection is also the account for the activities. And more than the 250 Kelvin, in such case, IC is 0. So in this case is Fujinami and Yasunari 2001 case. And he modifies this original convective index. And ICD is the TBB is the 00 UTC minus TBB is the 12 UTCs to take into the account to the diurnal variability. Convections day and night variabilities. It's like this. So after that, and they demonstrate the seasonal changings, the convective activities with the diurnal variations. So, and during the winters and January, February, such kinds of activities relatively is lower. But after the monsoon's onset, this occurs March, April, May, June, and amplitude of the and IC with the diurnal variabilities is also increase. So such kind of the simple analysis, we can capture the cloud activities like this. This is only the one and thermal band 10 micrometers band can be used, but we can monitor the cloud activities behave, particularly for the diurnal variations, because the convections and in the atmosphere, particularly convections over the land with the strong diurnal variabilities characterized. In such of things, is a geostationary meteorological satellite is a powerful tool to monitor this. So, and the next one, I will show the Hofmehler diagram. This is a time longitude cross sections. This is a y-axis represent the time. So satellite data slicing with the time. X-axis is the longitude. So here is the monthly and cross sections. 1 month. This is a start is from here to the end to the years. Data slicings and captures like one image. It's like this. And the figurings, like this is a Hofmehler diagrams, you can see how cloud move to the easterly or westerly is moving. So that's the reason why we think that this thing, the Hofmehler diagram, is very useful to the how cloud is moving. So in the case, this is in the case of the and in the equatorial zones. So here is the okay, this case is the easterly is moving. Mainly and main cloud and cluster is easterly is moving, but some part and it seems like the westerly is moving. Very complex reactions can capture by using the time longitude cross sections. So this is a very popular way to and shows how cloud move in the atmospheres by the geostationary satellite. This is very popular, so say to the Hofmehler diagrams. And another case is that this can applied into the latitude case. Northward moving to the southward moving case. In such case, x-axis represents the time. Y-axis is represent the latitude. Captures like this. Then, and easily to the monitor, the cloud movement is the northward or the southward movings. Such kinds of the simple data analysis help us how to cloud behave and through the observation of the geostationary satellite. So this is another example. Okay. So, and another thing that I'm talking about the use of the visible because of the visible wavelengths. This is the same wavelength of the human eyes captures, and 700 meter to the 700 and micrometers to the 400 and micrometer to the 700 and micrometers is the visible wavelengths, and can capture the low level cloud. This is a zoom up image of the two different wavelengths. And left side shows the thermal infrared 10 micrometers IR image. Okay, please see here. Blue circles area is both thermal infrared and visible wavelengths and image can see as a white. So this area shows the high level cloud, highly developed cloud. This is brightness temperature is very low, and the cloud with so many and cloud particles becomes to the high reflectivities. So in such case, both thermal infrared and visible wavelengths looks like the white. And on the other hand, and red circles area shows the difference between the thermal infrared and the visible wavelengths. In the case of the thermal infrared, here is hard to the difference between the background and the cloud because of the very low level cloud in elevations. So in such case, brightness temperatures difference 10 micrometers represents the cloud top temperatures or surface temperatures. Low level cloud means the brightness temperatures difference is very small. So the hard to detect the cloud. On the other hand, visible wavelengths. And during the daytime, you can see, you can easily recognize the cloud because of the cloud is high and reflectivities due to the cloud particle. So, and by utilize the visible wavelengths, assist of the sunlight, you can see easily the clouds, like a patchless cloud can detect compared with the thermal infrared. That's the reason why we use the visible wavelengths detects low-level cloud. So even though the daytime can capture, but this thing is very powerful. So, and this is one example is a cloud coverage and revealed by the GMS5. This is 2 generations before of the current Himalayas. However, and this is a visible wavelength threshold method, and how many cloud coverage is also occur during the daytimes. So around here, relatively high cloud amount, and mainly due to the ITC's part. And the mid-latitude area is also and Rossby waves area is also relatively high. And this is quite similar with the thermal infrared and threshold methods. And also, and this visible wavelengths spatial resolution become to the more improved compared with the thermal infrared. So, and you can see around here, and hopefully you can see here, and you can see the island. So island induce the cloud, even though the small island, it's become to the trigger to generate cloud in the low-level cloud. Such of the low-level clouds is also can capture by the visible wavelengths. It's like this. And the left one, it shows the difference between the cumulus cloud. I'll mention later how to distinguish cumulus cloud and the total cloud number. It's like this. And this is also another way to the cloud number of frequencies. So, okay, and let's move on to talking about the combinations usage of the visible and thermal infrared. So, and thinking about the wavelength difference and these things and thermal infrared versus the visible wavelengths and this two-dimensional diagram is so easy to diagnose the cloud type. For example, so in the visible wavelengths, it also sees the brand reflectivity is also high, and the thermal infrared is become to the more cold. Low temperatures case is detected in the tops of a big convective cloud. On the other hand, the infrared and wavelengths and brightness temperature is not so the high level, but the visible wavelengths, the reflectivity is relatively high. In such case, and middle level convective cloud. So this kind of the difference and attributed to the cloud type difference can capture. And I'll mention this is classification's result later. And another possibility to the cloud classification is utilized the bright temperatures difference around the 10 micrometers. So, and this schematic illustration is and split windows brightness temperatures difference and 11 minus 12 minus 11 micrometers to detect the thin cirrus or dust. So such kind of the very near wavelengths, for example, 10 micrometers versus 11 micrometers, 10 micrometers versus 12 micrometers, very close to the wavelengths. Even though the close to wavelengths, brightness temperatures difference can captured due to the materials emissivities difference between the cloud and the dust. Such of the emissivities difference in the thermal infrared regions can utilize the materials detections of the thermal infrared band using the split window to say the brightness temperatures difference 10 micrometers minus and 12 micrometer or 10 micrometer minus 11 micrometers. So such kind of the brightness temperatures difference and around the 10 micrometers easily to utilize the what kind of the component is available in the atmospheres. So, and okay, one example I will show the classification of the cloud. And ISCCP's cloud classifications. This is the most and popular classifications method by the meteorological satellite. This is ISCCP is an international satellite cloud climatology project. So, and this is based on the satellite data is how to monitor the cloud type and quantitatively. So this is a and same principle utilized. And the visible wavelength is utilized as the x-axis, thermal infrared y-axis. But this is changing the terminologies. And the y-axis represents the cloud top pressure. To say the another word, the cloud top pressure means the cloud top height in the atmospheres. And x-axis shows that this is so the not so the reflectivities and changing its term is the cloud optical thickness. Okay. In the case of the precipitatable cloud, you can see from the ground, just now is a rainfall is occurs. And in the surface, and there is daytime, so the sunlight becomes the shrinkings due to the how many, so many the precipitatable droplet. So in the case, the cloud optical thickness is increasing. So, and to say another word, the cloud optical thickness is become to the more big, big, and cloud optical thickness means the more severe cloud can capture in such case. So, and y-axis also the 60 in the cloud optical thickness and the relatively high level cloud, and classification into the deep convections. And the case is and relatively low, and optical thickness is also and small case. This is a cumulus cloud. So such kind of the 9 type typical classification can do by analyzing the geostationary or another satellite data. So, and this is a climatology of the Isccp's D2 data. And the left side and slide shows a very rough and image and total cloud amount of the globe. So ITCZ and relatively low in the Sahel regions and the tropical areas is like this. So, and compared with the previous one, this scans the classifications into the 3 levels, and high level cloud, and the middle level cloud, and low level cloud. So high level cloud is the ITCZ type and relatively high, and the middle level cloud is and around the southern part is a concentrate, and the low level cloud can concentrate to the eastern part of the oceans due to the ocean circulator, relatively low and sea surface temperatures, small difference between the atmospheric temperatures versus the sea surface temperatures, and also suppressing the air and air motions and makes the low level cloud. Such kind of the cloud properties difference can captured by the geostationary satellite combined with visible and thermal infrared dataset. So this is one examples. The another thing is the material for the split windows applied for the one example. This is a Shinmo eruption case. Okay, see the movie says this movie represents the 10 micrometers IR1 to the image, and here is the split windows IR1 minus IR2. So here is the eruption of the Shinmoe can captured by the MTSAT data. And to see the carefully, and you can see the eruptions data, but easily to visualize the difference between the IR1 minus IR2, 10 micrometer minus 11 micrometers difference due to the material difference of the cloud particle versus and dust from the eruptions. Okay, you can see. Okay, now here's. So such of things is easily to visualize and the cloud and difference between the cloud or dust layers difference. Such of behave capturing is one of the important tasks for the geostationary meteorological satellite. This. Okay. So another way is to utilize water vapor and thermal infrared. And this is also the difference between the 10 micrometer and minus 7 micrometers. And this is one example is the difference comparisons between the delta TBBs and around 0, 10 micrometer minus 7 micrometers around 0 is the huge amount of the water vapor is also available. And thermal infrared and the brightness temperature is low case. This means potentially capture the precipitatable cloud, captures like this. So, and they utilize this is delta TBBs and IR minus water vapor channels, 7 micrometers, is a proxy of the precipitatable cloud. Then, and they make this fantastic and psychedelic figures. And angle represents the peak time of the delta TBBs. This meaning to the and upper one is 0 local time. So this is analyzing the analogy of the clock. This length is 6 local times. So this and amplitude represents the length of the arrow. It's the amplitude of the delta TBBs. And the direction is a peak time, is the local time. So this is a very interesting result. And also such kind of the utilized water vapor is very useful to the precipitatable cloud or another cloud distinguish. This is one example. So and in the point of view to the operations for the meteorological agencies, the capture the wind speed based on the difference, the seeing of the geostationary satellite. So, and pattern matchings between the previous time and the current time, and easy to capture the cloud. Then, how to move the cloud, getting the data, and which height moving the cloud. These things automatically detect the, and based on the cloud behaviors, getting satellite-derived windows. This is atmospheric moving vectors product. It's one of the popular product in the operational agencies. This is one example, the upper levels, and wind speed and wind direction, and lower levels, wind speed and wind direction. Such kind of wind speed and wind directions information is crucially useful for the weather forecasting. Because of the wind speed distribution, it's directly and contribute the improving and weather forecasting. That's the reason why another reasons. Operational agencies operating the geostationary meteorological satellite to getting the satellite-derived wind. Because such kind of the satellite-derived wind directly improve the accuracy, the forecasting skill. This is the reason why. And the second ways. So anyway, and Chiba University's Center for Environmental Remote Sensing is one of the center for the getting the geostationary meteorological data. And we have the activities for and the virtual laboratories. So we collaborate with in the Japanese researchers and the modeling, numerical modeling people, and the CO2 observations expert, and the waters management people, and we, Center for Environmental Remote Sensing, is the expert of the satellite data handling and analysis. So, and we collecting the geostationary data not only for the Himari, but also the GOES and the Meteosat, UMETSAT, and also the Chinese satellite. And we getting data and that also converted like this. You can also getting the data, such kind of data set, and through the anonymous FTP. And we have and since the start of the Himari 1, and the first generations, the years, to the current Himari 8, more than 30 years data, we getting the data, and anyone can access and easily to the handling analysis, not only for the Himari 8 and the and goes east and west data, and FY2 is a Chinese satellite. Is also we can getting the data, and also we release data. And if you want to use the data, please contact us. And this is like this. So, okay, and let's move on to the main topic. So, and I want to talking about the third geostationary meteorological satellite, and currently is Himari 8. This is the latest version of the geostationary satellite. So how advantaged that I will introduce these things. So, and the Japan Meteorological Agency have long histories to operate the geostationary satellite. And since July 1977, and the first generation GMS-5 to the continuously, we have the GMS 1, 2, 3, 4, 5. But and unfortunately, here is the big mistake and fail to the release satellite. So we lent the GOES 9 and from the NOAA and replace the data. And after that, we getting the MTSAT second generation data. This is the Himari 6 and MTSAT 2 and Himari 7. So currently nowadays, the Himari 8 and Himari 9 is a standby satellite. Both two satellites is and available in the space. So, and Himari 8 and 9 is located the position is around the 140 longitude in east. And this was and to start the operation in the 2050s, and currently is more than the 5 years operations in the Himari 8. And Himari 9 is released, launched in the 2016, now in the standby satellite. And also after the finish, the Himari 8 finished, and plan to the 2022 switch to the Himari 8 to 9. And currently, JMA plan to the 2028, and the Himari 9 will be operate. So more than the 50 years, and we will be can get the data. So, and compared with the previous ones, and we have the Himari 8 the improved resolutions, and very easily to see to the, for example, the visible wavelength is a previous satellite is only one band. To say this thing is a monochrome image can get. And currently the Himari 8 and 9 has splitting the 3 band in the visible wavelength. And red, green, and blue, this makes the two color image generations. Not only for the here, so the so many band also include. And especially the spatial resolution is the previous one is 1 kilometer, but currently we have the 0.5 kilometers and 1 kilometer in the visible and the near infrared. And also the thermal infrared spatial resolution is 4 kilometers to the 2 kilometers improved. And the temporal coverage, observation coverage is also greatly improves the previous one. And because of the previous one is once per 1 hour's observations. And this is means the 30 seconds observations interval will be required and the previous observations. But currently is 10 minutes interval, full disk scans is available. It's so very to visualize to compare the previous one. And previous one is the like the how to say so the slideshow like, but currently Himari 8 is very smooth compared with the previous one. So this is a difference. And the spectral band is also improved like this. And not only for the visible wavelengths, we have the near infrared band. It's the near infrared around here, and the 10 and 1.6 and 2.3 is available. And so I'll mention later, so around the 7 micrometer and the split into the 3 band. So this is getting the data is increasing the water vapors band. This is very useful to detect the water-related information compared with the previous versions. And also, and submarine infrared area is also band, also increasing. Getting the data is a more split window, bright band difference information is more utilized. It's like this. So anyway, I skip like this. And observation, it's also the very variable with the current versions. And full disk scans and detected whole of Earth is a 10 minutes interval. Within the 10-minute interval, and Himari 8 scanning the Japan areas, 2.5 minutes interval. Very fine resolutions. And also the target area is the mainly targeted focused on the typhoon target. And also can capture the 2.5 minutes. And also, and landmark, this is, and usually can see, but very fine time resolutions can data currently can getting Himari 8 and third generation satellite. Anyway, so I will show the several movies to demonstrate to images like this. Firstly, I will show the beautiful full disk true colors image captured by the Himari 8. So this is a day and night combined versions with a 10-minute interval. So very smoothly it captures the data and the day and night times. So particularly the day times and true colors image can getting the data even though the geostationary meteorological satellite. So firstly, and first impressions I get in the data and just before the operations, and I feel very beautiful. Earth is very beautiful and very impressive image can getting. So not only for the Himari 8, currently is NOAA operates the GOES R and GOES S. This is a similar satellite of the Himari 8. This is GOES 16, GOES R. So this is a GOES S, GOES 70. So says another one, GOES West. Also can capture the similar image with a 10-minute interval. So very beautiful the image, not only for the Himari areas, but also for the North American, Latin American regions currently can capture. So very beautiful. Okay, let's move on to the next and very beautiful the clouds movies and beautiful Kalman vortex captured by the Himari 8. You have to see that this is a band Kalman vortex and waves like this. And this is a texture is very beautiful. And below and this side of the Jeju Island, this is Korea's. Okay, changing the next days as atmospheric conditions will be changed. To show the Kalman's vortex is quite different and beautiful and image movie can see. And also, and this is, I will show to the thermal infrared 10 micrometers image. And this is says naming this as many gravity waves triggered by the convections observed by in the Australians. Okay. So here is a thermal infrared image. Day and night temperatures changing. So can you see the wave propagations due to the star triggered by the convections? Can you see the across the coastline, or how to say the orography? So such of things is also captured by the Himalayas 8 due to the shorter time scale intervals, 10 minutes interval, and also the spatial resolution also improved compared to the previous one. So many waves in the atmosphere is occurred by the convections. Very interesting and movies, these things. So even though the one band, the 10 micrometers, easily can capture such as very interesting phenomena. Okay. Okay. Next, I will show the movies is the water vapor channels, RGB's composite. So, and I say to explain the water vapor band, 7 micrometers splitting the 3 band. These 3 bands of data is assigned to the RGB's colors. In such case, the RGB colors represent the water vapor's vertical profiles difference. Easy to visualize more in the water vapor's difference. So this is a typical case and meteorological low and high activities. So here is the relatively and dry areas due to the frontal activities passed away. And frontal activities, southern part is relatively warm and water vapors warm and humid air is occurs, and the northern part is relatively cooler and dry air mass. It's the contrast in the typical and movement is the frontal activities. Such of things can easily to visualize the splitting the water vapor channels into the 3 band. So this is another and the possibilities to the water vapor channels splittings. Very interesting. But see the carefully is that this is a 2 and frontal activities difference, but each component's main feature is also the same, but in detail, a little bit difference in the 2 cases. To see the carefully is around the here is a complex the air masses difference, and the cooler or dry air mass and the moist air mass, the interactions. It also can see from the RGB composition in the water vapors band. It's also the interesting. And another case is RGB composite is water vapors band is a diagnose air mass difference for the monitoring. And this is the case is a westward moving the typhoon case. Okay, this is the case of the typhoon 12 and recent in the 2018. So this is RGB composite. So relatively dry air mass, it occurs. The easterly is moving like this. Typhoon is picking up such kind of the dry air mass and clockwise movement. So these things can easy to visualize RGB's compositions. This is another example with water vapor's behaviors. Okay. So, and another things is the monitor is aerosol. And the forest fire case is Siberia in the transport dust case. So this is a case is in the Siberian dust, and you can see it here, like this. This is a dust. So true color image is very easy to recognize the distinguish the dust and cloud compared with the monochrome image. Okay, see the carefully. In the case of this and dust event, dust moving above the cloud layers. Can you see? Here. Such of things easily to the captured by the true colors image. And also, and this is my favorite movie, and to demonstrate the Himari 8's capabilities. And this case is and true colors RGB compositions. And the forest fire in the North Korea in the atmosphere's environment changing dramatically due to the forest fire's smoke. Okay, firstly is, yeah, here. Biomass burnings, it occurs in the North Korea. In the next days, so atmospheric conditions become to very and dust noise in Japan, and see the carefully here, around here, can change the dust into the cloud here now. So, and I'm talking in the lecture is dust is the seed of the cloud. But here is very easy to visualize the changing from the dust to the cloud. And the next day is the environment, very hazy environment. And also due to the seed of the aerosol in the low level cloud, it's generated like this here. So before and after and forest fires, atmospheric conditions drastically change. This behavior is easily to capture here. Like, okay, again, this movies. Here is forest fires. In the next days, atmospheric conditions become to the dusties. And say again, here is a dust changing into the cloud. Yeah, here, now, it's a changing. So in the next days, a low-level cloud also occurs due to the seedings of the aerosols. So such kind of the atmospheric conditions, environmental change is with fine time step can captured by the Himari 8. This is a very powerful tool to monitor the atmospheric environment. Okay. So, and I will stop to the movie so that I demonstrate the examples. And firstly is, and we, Chiba universities, installed the 6 and 4K displays, big displays to the monitors. The current situation, current movie of the Himari 8. It was a very beautiful Earth status can capture in the Chiba universities. If you have the opportunity to visit the Chiba universities, and please come to the libraries, and you can see the movies. And the other case, and we have the YouTube channels, and including today's and the movies, and Dr. Toyoshima, and he is my colleague of the Chiba universities. He and generates and established the YouTube channels and the beautiful Himari 8 movies. And please and visit this site, and you can see the and beautiful and interesting movies captured by the Himari 8 or and Gold Sea satellite. So you can also and current real-time Himari movies and NICT's National Institutes and Communication Technologies and National Institute in Japan and developed the Himari real-time web. And this HTTPS himari.asia is the and very powerful interactive and applications to capture to see the current and the past and Himari image. And our team is also collaborate with the NICT Science Cloud teams, and 2 papers already published. And about these things, there's a Murata et al. There's a basic component, and next 2020 papers, so the international collaborations and the problem and the advantage, and describe these papers. Case. So, and we introduced our activities, and satellite data is also the need to the geo collections. And this is one example. And Himari standard raw data is even though the Himari 8 has a good quality of the geo collections, but we also apply to the more and precise the geo collections product, and we call to the geolocation collections. And with this papers, this is a description of the algorithm. Then we release data, and Himari 8 itself is the and the sphere-like dataset is provided by the GMS, but it's hard to the handling the data for data analyzing. So, and we combined with the precise and geo collections, and we say this is a gridded dataset, and longitude geo collected gridded data is like this, and we release the data. And please visit. This is and the website is a release note. How to getting the data, how to read the data is available, and you can see the data. As this is a baseline product. Anyone can access, and anyone can data handlings. Utilize this one. Okay. So, and I will demonstrate the several examples. And this is my group's student work. And 2.5 minutes behavior is a geostationary satellite. It's very suitable to the cloud activities, particularly for the one cloud and lifetime detections. So, and Himari 8 with the Japan areas observations, 2.5 minute observations like this. And also, our group installs the phased arrays weather radars. This is the latest versions of weather radars. This means to the 3-dimensional and volume of the and precipitatable the echo with the 30-second interval. Very ultra-fine time resolutions data we can get. So gatherings, these fine time resolutions. Then we got a better understanding of the behavior of the precipitatable cloud. We demonstrate these things. So, and this is one example. In the upper one is the Himari 8 detect the cloud properties. And this is the and red line indicates the optical depth of the captured by the Himari 8. and the black line reflecting the visible reflectance, and blue line indicates the effective cloud radius. It's like this. And lower panel shows the time height section and captured by the phased array weather radars. And time zero is normalized to the first echo detection time by the phased array radars. So just before the detecting the phased array radars, cloud is also developing like this. So visible waves reflectance is gradually increasing, and the optical cloud depth is also increasing, has a peak just before the radar's detections. After that, rapidly developing phase in the phase array radars within the 10 minutes, very fine times, the rapidly developing. After that, and develops and precipitation cell and precipitatable particle started the fallings like this within the 10 minutes. So this and time interval set as one cloud life can capture in this case. And also this thing is interestingly synchronized with the visible wavelength reflectance decreasing. So here is the falling life stage and also synchronized. The visible wavelength reflectance is rapidly shrinking, decreasing. This is corresponding to the falling down. To say these things, in other words, Himari 8's behaviors, 2.5 minutes intervals reaction captures one cloud's lifetime's behaviors. Very interesting. This thing is new generations. And even though the geostationary satellite can capture one cloud life's behaviors, this is very surprising things. So also we try to estimate the rainfall amount and from the Himari 8 estimations. And this is another research is our groups. And Hirose also is we utilized the machine learnings. And based on the random forest is one of the machine learning method. So in such cases, and one thermal infrared band case and rarely can capture the low-level cloud, but the intensively is falling rainfall case. This is a line shapes the heavy rainfall case in Japan. So this case is a cloud height is relatively low, but the rainfall intensity is very high case. It was and general case, it was hard to detect. So but we can utilize the multiple band, particularly for the water vapor channels. It was very for the utilize the low-level cloud detections because it will capture the water vapor's vertical profiles and from the Himari 8 data. So these things are statistically, and we getting the data. This and y-axis shows to the water vapor's windows around the 7 micrometers split windows data. This means the and 6.9 minus 7.2 represent water vapor's profiles differ and water vapor's vertical profiles related to signals. X-axis shows a 10.4 minus 12.4 the split window brightness temperatures difference. This meaning to the close to the zero is optically is high cloud can detect. So this combine the two informations. Relatively, rain rate high and intensive rainfall can captured with around and 0 and degrees in the 10.4 and 12.4 and brightest temperatures, and also difference between the two boundaries around 0 and plus case, relatively high and precious. This and brightness temperatures difference, particularly for the water vapors case, this can represent the and lower this and panel shows to the x-axis is the and brightness temperatures water vapors difference, and 6.9 minus 7.3 water vapors channels. So, and around the 0 and the plus case, and the vertical profile of the relative humidities here. This area is represented the, in this case, upper atmosphere is a relatively dry conditions can capture. Such kind of the contrast between the upper atmosphere and the lower atmosphere is water vapors contrast enhanced the and the precipitable amount with the low level cloud. So, and this result is very suggestible to the improve to the heavy rainfall detections by the geostationary satellite, particularly for the third generation satellite. So now we applied this methodologies into the whole of the Himalayan area, is the particularly for including the tropical regions. And also we apply to the pattern matching method. This is a kind of the and satellite data analysis basic method. So now we and prepare the paper to the and check the performance for the random forest machine learning method estimations of the rainfall and by the Himalayan 8. Okay, let's skip these things. And another thing is this is and the difference case is dust event detection by the Himalayan 8. This is and the Miyamoto et al.'s papers case. And this case is a dust and event occurs around the Mongolians. And left RGB slide shows this pink color indicates the dust RGBs. And this means the brightness temperatures difference and 8 micrometers, 10 micrometers, 12 micrometers, 3 band brightness temperatures difference and assigned to the RGBs. So, and this is also the easy to visualize the dust event compared with the previous one. So, and this paper is and successfully captures the dust movings, dust event frontal movings to the and eastward, like this. The another case is in the shortwave infrared band utilized for the preceded thermal anomaly is volcanoes thermal observation, volcanoes eruptions case. This is a Kaneko et al.'s and Earth Planet's so-called EPS papers, 2018. They focused on the 1.6 micrometers and 2.3 micrometers and the difference and between the normal case and volcanoes eruptions case. In such cases, and corrected case here. So the and more and volcano eruptions oriented the and abnormal signals can captured by the Himalayan 8. So increasing band and also the observation frequencies increasing also can apply not only for the weather observations, but also the and disaster event, such as the eruptions or dust events, something like that. In addition, okay, and I will demonstrate, I will show the example in the apply this data into the terrestrial research, particularly for the terrestrial vegetation research case. So here is one of the famous papers, Miura et al. In the scientific report. They demonstrate the time series is the cloud-free surface conditions data. Here, this is Himari 8 vegetation index case. And lower one is a Suomi MPP, the one of the typical polar orbit satellite. In the lower case, in the hard to detect is a seasonal changings. However, and Himari 8 has approximately 50 times the observations opportunities increase. Then easily to the can captures and seasonal and changings of the forest and temporal forest. And also recently our group and NASA Ames Hashimoto-san and published a paper in the Nature Communications in the behaviors of the and Amazon's rainforest and analysis of the GOES-R and advanced baseline images. So they demonstrate even though the tropical rainforest and can utilize the geostationary meteorological third generation's geostationary meteorological satellite data, can get the cloud-free data, can definitely capture the seasonal difference of the tropical rainforest's behaviors like this. So this result is very interesting result and also the insight, the understanding the behavior of the tropical rainforest and the phenological reactions. This is also apart from the weather observations. That's one of the potentially utilized and result. Okay. So another thing, I also mentioned one examples. This is a case is in a typhoon landing case. Unfortunately, 100 people passed away due to the landings and the floodings in Japan. This is record-breaking the typhoons and outbreak. Then, is Himari 8, just before and after the landings in the typhoon past. This is before the natural colors image, and this is after the landings, typhoon. So, and this blue colors area, blue or purple line colored area is represents a kind of the flooded areas. And because of the 1.6 micrometer is sensible for the water bodies. So, and natural colors utilized as RGB is 1.6 micrometers. So, according to this result, we estimate the normalized difference water index to detect the flooded areas. So, and this is one example, the NDWI's estimation, the detection of the flooded areas. This blue area is detected by the NDWI, so the estimated from the Himari 8, and the red colors shading areas. This is a validated data and based on the fine and spatial resolutions SAR data. So, and this says to the if the Himari 8 is ready for the flooded areas detections and across real times, and we can request to the low-level orbit satellite observations request due to the here is the flooded areas. Oh, very this is amazing the flooded areas, and rapidly have to observe the current situations. So in such case, Himari 8 or another third generation geostationary satellite may be and possible to assist the observations request. So this is one another and potentially is utilized for the third generation satellite. Okay, this is the final one. In the also and Miura-san and apply to the NDVI, normalized difference, NDVS difference in the Himari 8 detects the landslide detections. Very interesting result. Because here is can only apply to the forest areas due to the high NDVS area is changing rapidly. In such case, landslide it's also occurred. So, and this is one good example. So another example, the utilized to the and Himari 8 or the third generation satellite data more utilized the disasters monitoring, the risk mitigations. One good example. Okay. This is the final ones. And the closing remarks as a message and from my talkings is very simple. And the third and the geostationary meteorological satellite, the enhancing the capabilities and monitoring the Earth environment, not only for the weather, but also the atmospheric, terrestrial. Today, I'm not talking about these things. And also ocean environment is another issue to monitors and Himari 8. So, and more utilization will be needed. So I think an integrated link between the geo and low elevation satellite, particularly in the case of the prompt monitoring of the disaster event or something like that, more and effective link will be required, I think. But and geostationary, third geostationary data is volume is very huge, unfortunately, very huge data. And 1 month's data is 3 terabyte, very huge data set. So how to handling is a crucial issue for the utilizations. Okay, that's all. Thank you very much.
Okay, thank you very much for the very interesting lecture from you. It more understanding about the weather observation, of course. And now we in the discussion section. For every participants that want to ask a question, please write down your question in the chat box, or you can raise your hand so we can allow you to ask directly. And now I think there is already some question in the chat box, and Higuchi Sensei can read the question and you can answer.
Yeah.
By you.
Okay, and I will answer from the Arif-san and 4 questions. And how to calculate the cloud optical thickness and cloud pressures from the Himalayas. And okay, and the first one is the cloud optical thickness is based on the sun reflectivities band and visible wavelengths or another near infrared band. It's also based on the radiative transfers models or and lookup tables and assuming the clouds, how many and cloud particles are available, then estimate previously. We estimate the lookup table or radiative transfers based on the method. Then estimate the cloud optical and thickness and effective radius and the cloud liquid water's amount. And also, cloud pressures from the Himalaya 8. This is also based on the vertical profile of the air temperatures. This is coming from the reanalysis data or objective data and provided by the meteorological agencies. In the case of the Japan, and Japan reanalysis project and product JERA 55 and another and operational agencies released data. For example, and European people's ECMWF is and measures operational agencies released in the ERA 5 and vertical profilings. Then, and combined with the brightness temperature is 10 micrometer and vertical profile of the air temperatures can get things the and cloud top pressures. This is the question once. Okay. Okay. So, and question 2 is how to identify the cloud, a cold and warm front from the Himalaya 8. And this was related to the blue and brown color is on the water vapor band. Yeah, this is the quantitatively and water vapor's band's difference and among the 3 band. So, and we assign the and difference between the more shorter wavelengths. It was sensitive to the higher level. Because of the, even though the 7 micrometers splitting the 3 band, only to the sensitive to the upper levels of water vapors. And the difference among the 3 bands changing, the wavelengths changing, so the sensitive height, it's the more lower and lower. So, and we, and easily to visualize to the, and how to say, and the RGB colors, blue and dominant colors represent the more upper level of the cloud is low, cloud's water vapor is lower. But unfortunately, this RGB composite is not so established in the operational agency. Only the we and our group assigned to the RGB to the water vapor band. Because, and I do not talking about today, so the, and this RGB composite widely is utilized because and Meteosat is the Europeans and the satellite agencies operate as a and Meteosat second generation satellite and the third generation FCIs also and have the plan to the third generation satellites. Only the 2 band available. In the case of the Europeans and the third generation are the 2.5 generations. This color is not coloring is the 3 band is not so popular. So this is a question 2 is so the and quantitatively so the simply we assign to the easy to the imagine. And the blue is the relatively dry air, and red color indicates the relatively is warm and humid airs colors assigned. Is a question 2. The answer is question 2. And this question 3 is, and it's very beautiful image H08 can capture from the dust to cloud. So how to know process from the dust to the cloud? It's several way we have. And firstly is the distinguish the and visualize by eyes in the visible wavelengths. And true colors RGB's image. And we can easily monitor by eyes the dust and the cloud is also very different and colors can see. And natural color is also utilized. The 1.6 color is also can easily to distinguish. Another way to the eye shows and one example. So this, and can you see that this is my slide, and this is RGB's image. This is a dust RGB. It's not so based on the visible and near infrared image. And this is based on the thermal infrared RGB. 8 micrometers, 10 micrometers, 12 micrometers, emissivity difference. Because of the difference in the cloud particle and dust particle, and the wavelength dependent emissivity is different. It's so easy to detect the dust. But however, and dust and aerosol is another issue. Dust is a very high amount, high density of the aerosols, but the relatively low and amount of aerosol case, it's so hard to detect is a thermal infrared. Because of the aerosol case is a wavelength dependent, it's very high. Shorter wavelengths easily to detect the aerosol, particularly for the sunlight-related wavelengths. More shorter wavelengths, it's also and detectable for the aerosol, not so dust. This is this answer is quite beyond the questions. Anyway, this is my answer is question 3. And 4 is the statistical analysis slide. How to know the pressures and R from the static R from the satellite. This what means R? How to know pressures IR, no R.
Mr. Arif, maybe you can explain your question.
Okay, thank you, Mr. Indra Gunawan. In my question, R is relative humidity. I'm sorry.
I see.
I see.
I see. Here.
Okay, thank you.
Here. Okay. Yeah. And this and left one's and analysis is based on the reanalysis. And data coming from the and ERA 5 and reanalysis data. It's not so the observations. So, and we getting the data, the case studies data is we getting satellite data and the corresponding vertical profiles from the reanalysis we combined into the here's getting the data. So color indicates the relative humidity is also one of the component from the reanalysis output. This reanalysis is combined with the numerical and simulations output and the observations with the data simulations. This is a virtual result. But such kind of a feature is also can support the evidence. This is answer is question 4. Is it okay?
It's okay. Thank you very much, Professor Higuchi.
Yes, thank you very much. Yeah, okay. Oh, 2 questions. Next question. Okay, thank you, questions. And what processing process must be conducted before the data can be interpreted? These questions, it's so hard to answer. And because it's so that this a kind of the preparation process, it's largely depend on the research target. And okay, for example, case the cloud detection or land surface behaviors detections target is opposite. So in the case of the land surface detections, cloud, we don't need removing. In the case of the cloud analysis, okay, cloud-free area, we don't need opposite sense. So, and this question is hard to answer. And this is largely depend on the target. I have to say. Okay, and 2. Okay, question 2 is the orbit for the geosatellite is very and compared with other satellite, what is its benefit? And most is important benefit is always capture the same face. This is a benefit. Always, so Indonesian people can get the always same face from the not only the JMA, but also the KMA. Korean is also similar satellite, also operated with the fine time resolutions. Even though the first generation is once per 3 hours, frequently observed. This is crucially important. The observed, the changings, the state of the atmospheres changing, rapidly changing situations. And particularly for the third generation satellite is a 10 minutes, or case of the Japan is a 2.5 minutes interval. It's also crucially advanced compared with the other satellite. This is the most benefit. So, and another case, and disadvantage is, so the one of the disadvantage is the spatial resolution. Because current situation is the most of the fine spatial resolution is 500 meters at nadirest. Now, and JAXA, Japan, and the space agencies and try to release the satellite with the fine spatial resolution with the geostationary orbit. This means that approximately 100 meters as a radius with a 1 hour interval. So this kind of design is also based on the depend on the sensors required. And say another words, and this advantage geo only can capture the same face. So this says another words the intercomparison or compared with the result of the Himari 8 with GOES R and Meteosat is the directly observe, directly and compare is the hard work because the face is different. This is a disadvantage. But currently, we and satellite communities try to the geo and geostationary satellite and the low elevation satellites and utilize for the calibrations each satellite more integrated usage. For example, Japan also has GCOM-C's SGLI this is one of the images and similar specification of the Himari 8. Try to the intercomparison in the signal with the low elevation satellite and the geostationary satellite. So we try to overcome the disadvantage of the geo. So I think the near of the futures and main observation consists of the geostationary satellite with and low level satellite with and I think the small satellite. Huge number of the small satellite is the observation will be the world of the and Earth observation, I think. Is this okay? My answer. Okay, and the next question is compared with this is the same one, and Next one is thank you for the presentations. And okay, I want to ask about the relationship between the wind and air pressure. What we know if the occurrence of the wind is a result of the changing the air pressure. Yeah, there currently the satellites that are able to calculate or predict the value of the air pressure as location on the Earth. Oh, very challenging issue this is. I'm not sure. I'm not see such kind of the analysis result. So, and very interesting result because and 10 micrometers animations see the and trigger and convection trigger like the wave propagations, maybe also changing the air pressures. So, and these things, and if you can do, this result can apply to the air pressure difference, particularly for the perturbations process with the turbulence in the atmosphere, and maybe you can get the Nobel Prize. So, and this is a big issue in the field of the meteorologies. The capture the gravity waves in the several scale is a very challenging issue in the meteorology. But I'm not yet and show the definitely such kind of the result. So very challenging issue, I think. Okay. So, and the last one is the how to integrate between the Geo and Leo and the SAR, and it's related with the assimilation. I see. And so many levels, I think, and Geo and Leo's integrations use. And I demonstrate one example is Geo is a baseline image and captures now. And in this case is a latency is so crucially important for the disasters monitoring. In such cases, we always ready to capture the and disasters event. Then, we can capture the such kind of event. Then request to the Leo's operational agencies. Okay, captures here. This is one possibility. And another possibility is Leo and Geo's and collaboration. It's so and I already mentioned about the calibrations among the Geo and utilize the baselines and Leo data. This is mainly based on the and optics and images. And another thing is combined and with data simulation. Yeah, you are right. Data simulation and interpolate even though the Geo cannot capture the event, particularly for the below the cloud, anyone can see the behavior. In such cases, combined with the data simulations techniques, and some researchers apply to the Himari 8 with the data simulations can release the aerosol dataset, even though the cloud covers areas with the data simulations technique, then generate the aerosol dataset. So such kind of the sense and bridging with the geostationary satellite data and data simulation and numerical simulation is becoming more familiar, I think. Now it's such kind of day. Very good questions. Okay, another questions. And hello, Higuchi-san, okay. And how you have any recommendation for the remote sensing data which has good temporal spatial resolutions about 1 hour around the 1 by 1. Yeah, Himari 8 is better. But Himari 8 is and thermal IR is and 2 by 2. And near infrared is also some part is 2 by 2. But And near infrared has 1 by 1 with 10 minutes interval. So currently, another options without geostationary orbit and with interval 1 hour is impossible. Combined with the data simulations, numerical simulations, and the data set is also available. Like a GS map is a combined product of the rainfall and provided from the JAXA is combined with the geostationary satellite and the microwave signatures. This will become the more popular, I think, the more combined data set. Oh, another question coming. Okay, thank you, questions. And because of the time durations, question is the last question. Okay. Okay, I see.
Okay, thank you very much, Higuchi Sensei, for the discussion. It's very interesting. But because the time duration, we have to end our class. But maybe if you have something to something closing remarks, you can say.
Okay, thank you. Enjoy it.
Okay. And before we end our class, maybe we can take our picture together, and then we can end the class. Miss Rifa, can you help, or Miss Harmita, can you help me to take the picture?
Okay, everyone, this is a photo session. Please open your camera and we will take a photo together. Okay. For the first page, say cheese maybe. First page. And then the second page. And then third page. And then fourth page. Okay, this is the last.
Okay, thank you, Ms. Rifa. And then this is the end of our class. And once again, we say thank you for Higuchi Sensei to give a lecture. It's very interesting. And hopefully we can meet in another occasion. And then we also say thank you for our participants in this class. And now we can close our class, and you might leave the room. Thank you very much.
Okay,
Bye-bye.
thank you very much. Yeah. Thank you, Atsushi-san.
Thank you.
Thank you. Okay, I end this meeting.